Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 21 from the course, but make sure you have watched the previous ones before viewing this one. So now we have learned quite many models related to the structure of atom, and we are into the last leg of journey into this course, wherein we are going to learn the model of the structure of atom which is being followed today. We will be learning about the quantum mechanical model of atom. So before we can understand what is the quantum mechanical model of atom, let us first of all understand what is quantum mechanics. And for this you have to understand first of all what is classical mechanics. Well, classical mechanics is the one which we are studying these days in physics, that is kinematics, laws of motion, work power energy, circular motion, motion in one dimension, two dimension, everything. So what do we mean by classical mechanics is basically that this is a branch of physics that is based upon the Newton's laws of motion, and this successfully describes the motion of all macroscopic objects like the apple falling from the tree, from where Newton derived his law of motion, then the orbiting planets which have essentially a particle-like behavior. So classical mechanics is functioning on the macroscopic objects, accepting that they have a particle-like character. But what happens in the case of microscopic objects? Well, this is going to fail as far as the microscopic objects are concerned, because it does not accept the concept of dual behavior of matter. And this dual behavior of matter as applied on the microscopic objects, this was given by Broglie and Heisenberg. Broglie said that the microscopic objects, they have like the electrons, they have particle-like and wave-like character. Heisenberg said that we cannot determine the position and momentum of an electron simultaneously because they have both particle-like and wave-like character. So here classical mechanics fail. And hence we have quantum mechanics, which is the branch of science which is going to take into consideration the concept of duality of matter. And this quantum mechanics, this is defined as a theoretical science which deals with the study of motion of microscopic objects that have both observable wave-like and particle-like properties. And this is going to give the laws which these microscopic objects obey. Okay. So when quantum mechanics, this is applied to macroscopic objects, the results are going to be the same as we get from classical mechanics, because the macroscopic objects, they have wave-like properties being insignificant. Okay, so we have studied all this while we were discussing the de Broglie equation also. For the macroscopic objects, the wave-like properties, they are insignificant, and hence we can apply quantum mechanics to this also. Okay. So now let us understand what is quantum mechanical model of atom, which we accept today as the model giving us an explanation, insight into the structure of atom. Well, quantum mechanics, this was developed independently by Heisenberg and Schrodinger, but here we shall discuss quantum mechanics based on the idea of wave motion as developed by Schrodinger. So Erwin Schrodinger was his full name, and he gave the fundamental equation of quantum mechanics, which even got him the Nobel Prize in Physics in the year 1933. And this equation, this incorporates wave-particle duality of matter. But this equation, as you will see further, this is going to be a quite complex one. This requires high-level mathematics, which is not possible for us to teach to a class 11th and 12th student. So that we will try to skip off those things which are requiring complex mathematics and try to understand basically what we get from all those equations, the results of those equations. So well, Schrodinger, he considered the electron to be a three-dimensional wave in the electric field of positively charged nucleus. And to completely describe the behavior of electron in this three-dimensional space, he developed a mathematical equation which we know as the Schrodinger wave equation. And this is the equation, I think quite complex one. So let us understand what all this means. So we have a delta square psi over delta x square plus delta square psi over delta y square plus delta square psi over delta z square plus 8 pi square m over h square into e minus v psi. So this, first of all, this sign which you are seeing for the first time, this is called as psi. So let us see what all these mean in this equation. So m we have as the mass of the electron. Then E, which you can see, that is the total energy of the electron. V is the potential energy of the electron, which is minus Z E square by R. And then H is the Planck's constant. Fine. So X, Y, Z, which you are seeing, these are the Cartesian coordinates specifying the direction and distance. Okay. And psi is a wave function representing the amplitude of electron wave. So let us discuss this a bit more. So this is the equation which was given to us by Schrodinger, and this is the wave equation which describes the electron. First of all, what do you understand by a wave? Well, wave is something, if you think, you imagine, the first thing that is going to come into your mind is something, a wavy line, like my cursor is moving up and down, right? So if this is a wave, this is associated with a wave function. For example, we have a wave with a wave function associated as sine x. So if you put the various values of x, 1, 2, 3, 4 and so on, you will get certain values. If you plot a graph of all those values which you are putting into sine x, you will get a graph of a wave. Okay. So this sine x, this has given us something about the wave, right? So when we are putting in the different values of sine x, we are getting different solutions. We are plotting them on a graph and we are getting a wave. So wave function, that is sine x, this has given us all information about a wave. And according to de Broglie, we know that electron is also a wave. So if electron is a wave and we know its wave function, we will get all the information about the electron, right? So this equation, this is giving us all the information about the electron. This psi, this is known as the wave function. So putting the values of psi, we are going to get all the information about the electron. Fine. Now come back to sine x again. So does sine x mean anything by itself? No, it is not meaning anything by itself. Does just simply writing sine x, do you understand that this is going to give you a wave? No, it is not. But when you put values of x into the wave function sine x, you are going to get the values giving you a wave, right? Similarly, the psi, this is a wave function. You put values into this and you are going to get certain results which will give us the information about the electron, right? Having understood this, we can now write the Schrodinger equation as h with a cap on it into psi. This is equal to E psi. Now what does this mean? Well, h here is the mathematical operator called as Hamiltonian. Now understand this again. Now, if h with a cap on it, the Hamiltonian operator into psi, this is equal to E into psi. E is energy. Does this mean that this h with a cap on it is equal to E? Well, it is not. Okay, let me give you an example. You all have done differentiation while you were doing basic physics. So if I tell you what is d by dx of e to the power x, I hope you are clear. D by dx of the e to the power x. Well, that is going to be e to the power x itself. So this means that d by dx of ex is equal to 1 into ex. So is that meaning that d by dx is equal to 1? Well, it is not. So you all can understand that d by dx, this is an operator, and when we are putting the values of e to the power x, we are getting some results. Okay. Similarly, this is h to the power h with a cap on it. This is an operator. When you are going to put various values of psi, you are going to get certain results in the form of energy of this system, the energy of the electron. And this energy which we will get, this is going to take into account the kinetic energy of all the subatomic particles, the electrons, the nuclei, the attractive potential between the electrons, the nuclei, the repulsive potential between the electrons and the nuclei individually. Okay, and this is the equation we have simplified and written it as this. We do not need to understand what all this. Okay, so here you can at least see that this Hamiltonian operator, this is going to give you a double differentiation of the coordinates in respect to the coordinates x, y, and z, and we are going to get certain values of energy. Okay, so this is what all we need to know about this Schrodinger wave equation, that we have a wave function psi. When we are using a mathematical operator, putting the values of psi, we get certain values, certain results, certain solutions which are going to give us the energy and other things about the electron. Okay. So the solution of this equation, they are going to give us E, and they are going to give us what all information we are going to need for an electron. One more thing that was left over here is that this is going to be for a system. This equation that we are writing over here, this is for a system which is an atom, a molecule whose energy is not changing with time. That is, probably we are considering about a free electron. When it is going to be time dependent, there will be certain more equations which we do not need to know. So we will not be going into the detail of these equations, but we will learn the results that were given by Schrodinger on solving these equations only. So what is the significance of this psi? So this is a wave function which is a solution to the Schrodinger wave equation. Putting the values of psi, we are going to get certain results which are going to give us a wave, right? And this is going to represent the amplitude of the wave. So if we put the results and form a wave, so with respect to distance and direction, we are going to get the amplitude of the wave. Okay, I hope this is clear. And then the values of psi, they may vary. There may be many values of psi that will be coming from those equations, and all these values, they may not be significant. The significant values which we will be considering, they are called as eigenvalues, and these significant values are going to give the total energy of the electron. And one thing more, please do remember that psi, it does not have a meaning of its own. Okay, only when we are putting various values for psi, we are getting some results. Then what is the significance of psi square? So for electron waves, psi square, this has a physical significance, and this represents the intensity of electron at any point. That is the probability of finding the electron in three-dimensional region of space. So psi square, this will give us the probability where we can find the electron, right? So we cannot exactly say where the electron is going to be. We can only say that there is a probability of finding an electron. So this is what which gives us where the probability of finding the electron is maximum, where the probability of finding the electron is going to be 0 or minimum. Okay. So this concept of psi square, this is going to lead us to the idea of orbital. And psi square, this is equal to probability density, and this is equal to probability by dV. Okay, so this is giving us the probability in a small space in a small volume. Okay, and probability you can say as psi square into dV, and this is known as the radial probability function. Now, having understood that psi square, this gives us the probability of finding an electron in the three-dimensional space, we come to the next important term that you have to understand: what is an orbital. So by now we know that it is impossible to know the position and momentum of the electron simultaneously with accuracy, and we have to talk about only the probability of finding the electron in a specific region. So this specific region, the three-dimensional region around the nucleus where the probability of finding the electron is maximum, this is called as orbital. Okay, and we cannot draw a real picture of the orbital. Sharp boundaries of the region of an orbital, they cannot be determined, right? So because we do not know specifically where the electron can be present, so real picture we cannot draw. Sharp boundaries of an orbital we cannot determine. But even then, if we want to have a shape of an orbital, what probably it would look like is, how would we do that? Well, we are going to represent the electron density in a region of space as given by the probability density by darkening each portion of space around the nucleus, and this is going to give us a diffuse cloud, and that would be the electron cloud representation of orbital, which I'll be just showing you in the next slide. Okay, so here we have is the electron density cloud. So what does this mean? This is not a real picture of an orbital. This is just a dot representation of the electrons where the probability of them can be. So this region around the nucleus where you can see there are many dots, this is showing that this region there is maximum probability of finding the electron. Then as we are moving farther away, you are seeing that there are less dots, and this means that in this region the probability of finding the electron is less. And now comparing an orbit with an orbital. Orbit, this was given by Bohr, and now we have the orbital as we understand from the quantum mechanical model. So orbit, this is a well-defined circular path around the nucleus in which the electrons revolve. Whereas orbital, this is a three-dimensional region around the nucleus where probability of finding the electron is maximum. Orbit, this is circular in shape, whereas an orbital, this is spherical, dumbbell or double dumbbell shape. An orbit is going to represent the electron moves around the nucleus in a flat plane. Okay, so this is basically a 2D picture, a flat plane, whereas an orbital, this represents that an electron moves around the nucleus in a three-dimensional space, which it actually is. And then orbit, this represents that the position and momentum of electron, this can be determined simultaneously, but as we know now that it cannot be. An orbital represent that the position and momentum of electron, they cannot be determined simultaneously with certainty. Maximum number of electrons that can be accommodated in an orbit is going to be 2n square, where n is the number of or the orbit, and maximum number of electrons an orbital can accommodate, that is 2, as you will be learning further in the course. So now, having understood all this, we can just quickly see what are the important features of the quantum mechanical model of atom. These are the results which we are getting from the Schrodinger wave equation. Because we cannot solve it, we cannot understand that high level mathematics, what all results that were given by the quantum mechanical model, we will just study those results and try to learn them as facts. Fine. So the first important feature is that the energy of electron in an atom is quantized, where the electrons are bound to the nucleus in atoms. The next is that the existence of the quantized electronic energy level. This is a direct result of wave-like properties of electrons and the possess permitted solution of the Schrodinger wave equation. So whatever permitted solutions are coming, they are giving us the various electronic energy levels. Okay, and that is what is showing that the energy levels, they are quantized, they are having fixed energies. And both the exact position and the exact velocity of an electron in an atom, this cannot be determined simultaneously. The path of an electron can never therefore be determined or known accurately, and we can only talk of a only relative chance of finding the electron with some probable velocity at different points in an atom. Fine, I hope this is now clear. And then we have an atomic orbital, and this atomic orbital we are getting as a result of wave function psi for an electron in an atom. Whenever an electron, this is described by a wave function, we say that the electron occupies that orbital. Since many such wave functions are possible for an electron, there are going to be many atomic orbitals in an atom, and these one electron orbital wave functions or orbitals, they form the basis of the electronic structure of atoms. And in each orbital, the electron will have a definite energy. So what do we mean from all this is that the electrons, they are present in some orbitals, and in an atom there are many orbitals, and these orbitals, they are going to have their own definite energy. An orbital, this cannot contain more than 2 electrons, and in case of a multi-electron atom, the electrons, they are filled in various orbitals in the order of increasing energy, as you will learn further in the course. For each electron of a multi-electron atom, there shall be an orbital wave function psi characteristic of the orbital it occupies. So specific values giving us specific orbitals, and all the information about the electron in an atom is going to be stored in the orbital wave function psi. Okay, so we are not going to understand what these wave function values are, but whatever these orbitals we are getting, now we get that an orbital are present in the structure of atom. The electrons, they are getting filled into these orbitals according to increasing energies, and in one orbital there are going to be not more than 2 electrons. That is all we are getting from these values of psi. The probability of finding an electron at a point within an atom, this is proportional to the square of the orbital wave function psi square at that point. Psi square is known as the probability density, and this is always positive. Okay, so because this is mod of psi square, so this is going to be always positive, and from the value of psi square at different points within a time, it is possible to predict the region around the nucleus where the probability of finding the electron is going to be maximum. This you will be understanding when we will be discussing the shapes of various orbitals. We will be plotting the graphs between the psi square and the radius, the region in which the electron can be present. So you will be understanding that better. So how we are getting all these values, how we are getting the shapes of the orbitals and so forth. So the characteristics of the wave function, which are very important, is that the wave function psi, this corresponds to an energy state and contains all information about the electron in the same. The wave function, this is a mathematical function whose wave depends upon the coordinates of the electron in an atom and does not carry any physical meaning. That is why the wave equation that you were seeing, it had all the coordinates x, y and z, because that is giving us actually the coordinates of the electron. Then such wave functions of hydrogen and hydrogen-like species with one electron, they are called as atomic orbitals. The wave functions pertaining to one electron species, they are called as one electron systems. The probability of finding an electron at a point within an atom, this is proportional to the mod of psi square at that point. And the quantum mechanical results of the hydrogen atom, they were successful to predict all the aspects of hydrogen atom spectrum, including some phenomenon that could not be explained by the Mohr model. Okay, so all this information that we are getting from the Schrodinger wave equation, that was able to explain the hydrogen atom spectrum. So now when we apply the Schrodinger equation to the hydrogen atom, this gives us certain solutions which give the possible energy level of the electron which it can occupy and the corresponding wave functions of the electron associated with each energy level. And these quantized energy states and the corresponding wave functions, they are characterized by a set of 3 quantum numbers. Okay, so quantum mechanical model giving us quantum numbers. These quantum numbers, they are going to give us the quantized energy states in which the electron can be present. And these 3 quantum numbers are the principal quantum number n, the azimuthal quantum number L, the magnetic quantum number m. And these are coming as a direct result of the solutions given by the Schrodinger equation, and these quantum numbers are what we are interested in to understand the electronic configuration of the atom. So the Schrodinger wave equation, this would give us the quantum numbers, the values of the quantized energy levels in case of hydrogen atom, and these are what we are going to learn further in the course when we will be learning about these quantum numbers in detail, because they are going to be very informative as we require the electronic configuration. But when we apply the Schrodinger equation to the multi-electron atoms, there is a difficulty. The Schrodinger equation, this cannot be solved exactly for the multi-electron atoms, and then this difficulty is overcome using some approximate methods. Okay, what is the basic difference in the multi-electron atoms and hydrogen-like species is that the energy of hydrogen and hydrogen-like species, there is only one electron, and this is going to be dependent upon the quantum number n. Whereas when we discuss about the energies of the orbitals in the multi-electron atoms, that is dependent upon 2 quantum numbers, that is n and l, as we will see further in the course. But then the approximate methods, they just helped us to understand the various energy levels in case of the multi-electron systems also. And then from that we were able to understand how the electrons, they are placed in the various orbitals even in the multi-electron system. All this is going to follow in the course now, and all this is going to be really very interesting. Only thing is that we found some difficulty in explaining the Schrodinger equation because we cannot see the results, we cannot derive the equations ourselves. So still, I think you will be able to understand that this is a wave function equation. Putting the values of psi, we are getting certain results. From those results, we are getting the values of the energies of the various orbitals into which the electrons, they are placed. And from that, we are going to get the electronic configuration of the atoms. So I hope you have found that this is going to be very interesting, knowing about the quantum numbers and the electronic configuration of the atoms further in the lectures. The next lecture is going to be on the quantum numbers. So I hope you're going to join me back for learning more about the quantum numbers. If there is any difficulty, please feel free to mail us at h2ochemistry@gmail.com. And if you've liked the lecture, do click on the like link. Also, do subscribe to our channel H2O and click on the bell icon to get a notification as and when we put up a new course for you, a new lecture for you. Thank you for now. Have a nice day. Enjoy yourself.